Hello, welcome back to Troubleshooting Python Application Development. In this course, we're going to teach you how to troubleshoot performance issues in your apps, whether that's your Python code not running quite fast enough, or it's taking up too much memory, or both. This video, we're starting a new section around tackling long-running loops and generally long operations on big lists of data, using a Python library, a third-party Python library called Numpy. In this section, we're going to look at the problem of processing large collections of data in 5 videos. Number 1, we're going to talk about the problem of using lists to perform vector calculations. Number 2, we're going to introduce Numpy arrays and how it allows you to do more powerful vector representations. Number 3, rewriting our problem with Numpy to speed up by 40 times, so a very dramatic speed increase. Number 4, fast MapReduce with Numpy broadcasting. And number 5, optimize all calculations in one go with NumExpression, NumExpr, which is a library that plug and plays into Numpy for certain optimization functions, which allows you to painlessly optimize the performance of your Numpy arrays even further. Let's start at the beginning. The first thing we want to look at is the problem of using lists to perform vector calculations. So what are vector calculations? Vector calculations are anything that is performed on a long list of data, right? Usually vector also means that that list of data only contains numbers, but actually you can also think of a long list of words, for example, or a long list of sentences as a vector of, or a data frame that you're processing. In particular, Numpy helps us speed up the case when our vector is purely a mathematical vector, i.e. it's a collection of numbers. So why is Numpy better? There are 2 problems with Python lists. So in Python, you can do many things with lists. You can see how long they are. You can put different types of elements in the same list. So you can have a list of integers, floats, and strings at the same time. And you can also add and subtract and move items around, or change the value of a particular item, or index and access a particular item in the list. To enable all of this functionality, a Python list is actually a list object that stores how long it is, some pointers to help Python allocate memory to the list, and then also a list of pointers to each individual element, each of which is a class, right, or an object. The reason that it needs to be an object for each of the elements is because each element can be of different types. So you need to actually store the type and the reference count of each element for you to be able to perform functions related to lists. In a very degenerate case, but there's a very long list, let's say 1 million items of the same data type, so 1 million integers in the same list. Python actually rather stupidly stores for every item in the million items its data type. So it has 1 million copies of the fact that this is an integer, right? So that uses a lot of memory, and sometimes when you're doing high performance optimizations, you don't need that kind of flexibility in your lists. So one of the things we saw in the other section is we can use a tuple to address this. In Numpy, this is addressed by having only one data type in the array. So in a Numpy array, you can only have one data type. You can't have 2 data types. You can't have a list that has integers and also string. It needs to be either strings or integers. Benefits of this is in Numpy, they don't store the object attributes of each element. Instead, because every element only differs in value but nothing else, there's a global storage of what does this list or array contains, and a contiguous block of memory allocated to values in the Numpy array. So because of a contiguous block of memory, it means that it's very easy to access elements in a Numpy array very fast, and also because it doesn't store for each element its type, it saves a lot of memory. This brings us to the other problem. In dynamic typing in the list, it introduces a large source of error because Python is also a dynamically typed language. When you're operating on lists, the addition function, for example, works both on integers and strings. If you have a list that allows any data type to slip in, it's very easy to introduce a bug where you are creating a list with a data type you don't expect, and because Python's functions are quite type agnostic, this error actually propagates through your code to somewhere much more downstream before it appears when there's a type error, or you're assuming that the result is a particular type, calls a function and the function doesn't exist. And then you're left with a big mystery on how to trace it back to where this item came about. With numpy arrays, because it's not dynamically typed, it's statically typed, it avoids this problem. You know that when you get it operate on a numpy array, there's only one type of numbers there, one type of items there. And all you need to do is make the correct assumptions with one data type and not many data types.